Hi students, I am Praveen Sebastian Paul. In this lecture, we are discussing a p-type semiconductor. So as we mentioned earlier, a p-type semiconductor is also an extrinsic semiconductor. So these extrinsic semiconductors are made with adding some impurities. That is, we are doping some impurities into the intrinsic semiconductor and make it as an extrinsic semiconductor. A p-type semiconductors are created by doping an intrinsic semiconductor with an electron acceptor element during the manufacture. The term p-type refers to the positive charge of a hole. As opposed to n-type semiconductor, p-type semiconductors have a large hole concentration than the electron concentration. In p-type semiconductors, holes are the majority carriers and electrons are the minority carriers. A common p-type dopant for silicon is boron or gallium. For a p-type semiconductor, the Fermi level is below the intrinsic semiconductor and it lies closer to the valence band than the conduction band. The different dopants for p-type semiconductors are boron, aluminum, gallium, etc. The band structure of a p-type semiconductor is shown in this figure. The dark circle in the conduction band are electrons and light circles in the valence band are holes. The image shows the holes are majority charge carriers. If the intrinsic semiconductor is doped with an electron acceptor, in order to make it as a p-type semiconductor, the electron acceptor is responsible for the formation of a hole by accepting an electron from the lattice. As a result, the majority charge carrier in p-type semiconductor is formed by the holes. In this way, the p-type semiconductor is defined based on its electron acceptor capability. In order to form a p-type semiconductor, the basic step is to dope intrinsic semiconductor with a trivalent impurity. In this type, the valence shell consists of 3 electrons, requires further 1 more electron. This is possible by sharing the electron. As it is accepting the electron, it is generally referred to as acceptor. The acceptor impurities are boron, indium and gallium. Once these are added to either silicon or germanium, p-type semiconductors are formed. So now let us discuss an example for this. A trivalent impurity such as boron or gallium are commonly used in silicon as doping impurity. Then the silicon doped with boron or gallium is a perfect example for a p-type semiconductor. A trivalent impurity like gallium having 3 valence electrons is added to the germanium crystal in a small amount. Each atom of the impurity fits in the germanium crystal in such a way that its 3 valence electrons form covalent bond with the 3 surrounding germanium atoms as shown in this figure. In the 4th covalent bond, only the germanium atom contributes 1 valence electron, while gallium atoms have no valence bond. Hence, the 4th covalent bond is incomplete, having 1 electron short. This missing electron is known as a hole. Thus, each gallium atom provides 1 hole in the germanium crystal. As an extremely small amount of gallium impurity has a large number of atoms, therefore, it provides millions of holes in the semiconductor. When the external supply of voltage is given to the p-type semiconductor, their majority carriers present in the valence band tend to move towards the negative terminal of the supply, and the minority carriers, that are the electrons present in the conduction band, move towards the positive terminal. In a p-type semiconductor, a large number of holes are created by trivalent impurity, and when a potential difference is applied across this type of semiconductor, the holes are available in the valence band and are directed towards the negative terminal. As the current flow through the crystal is by hole, which are carriers of positive charge, therefore this type of conduction is known as positive or p-type conductivity. In a p-type conductivity, the valence electrons move from one covalent to another. The electrons available in the conduction band of the n-type semiconductor are much more movable than holes available in the valence band in a p-type semiconductor. The mobility of a hole is poorer as they are more bound to the nucleus. Even at the room temperature, the electron-hole pairs are formed. These free electrons, which are available in the minute quantity, also carry a little amount of current in the p-type conductor. Hence, the current in the p-type is because of the majority carriers in the valence band, and a little amount of current is in conduction band because of few electrons that are their minority carriers. So my dear students, these are the basic principles of a p-type semiconductor. So as we mentioned, a p-type semiconductor are created by doping an intrinsic semiconductor with an electron acceptor element during manufacturing. So my dear students, hope you had understood this topic. So dear students, kindly go through this assignment question. Our question is, write notes on p-type semiconductor. So dear students, in the upcoming lecture, we will discuss what is a p-n junction diode. So dear students, see you soon. Until then, goodbye, thank you, and all the best.